Welcome to Physics 2211 Lab 5 Human Rocket by Blake Schwabe. The purpose of this lab is to explore the longest jump of nearly 39,000 meters and broke the sound barrier, and to try and use what we have learned this semester to try and figure out a more complicated problem. Formulas to use: Newton's second law, force equals mass times acceleration; Newton's third law, reaction force equals opposite reaction force; drag force and gravity; net force, the addition of all forces together. And then the preview: knowing from all previous experiments done, there will be a slight issue with the data from the experiment because of human error, but will give great insight into what goes through doing this insane jump and how much has been learned throughout this semester. Conditions for this lab: I used Lab 2's code as a baseline. I used the website given to me for the bulk of the information for the jump and the conditions. Finding the rest from other sources, like he pulled the cord from 2,567 meters from the ground, and he had a maximum speed converted to meters per second at 377.1 meters per second. Jeez, that's gotta hurt. Additionally, the temperature when he pulled the cord was 271.46 Kelvin, and Kelvin's used to make it a bit easier. And finding the change of that over the time, I got a time of about 0.266. And also needed to find B in the code, where B was equal to C times A, with C being the coefficient of drag and A being the area of the falling object, with the mass of the system being around 117.78 kilograms, roughly. There's no exact figure that I could find. The gravity being 9.8 meters per second squared, the terminal velocity being 377.1, and the rho being the air density where maximum speed was achieved, which was now 0.025, which was, when plugged into this equation, gives us C times A, which is around 0.644. Figuring out air density. This is needed since the density is changing throughout the time. We need to figure out a formula to use the air density, which is this formula right here, with PO being air density at sea level, capital PO being pressure at sea level, T being the temperature, and H being the height above the sea level. And these are the ones given from Google and previous ones used. So coding. I had all the conditions within the previous slides into the code and correctly added the equations into the system with T to fit the changing in temperatures as he was falling to Earth surfaces as he was heating up. You can see this with E, G, PO, capital T, capital PO, delta T. B is changed to the correct form. Time was changed to 260. And then P was changed, and then force of gravity, and the drag force was changed to actually have this all working. So this is the results that we have. The final predicted position is 2,860 meters, which isn't that far off, but the maximum velocity predicted was around 290 meters per second, and of course I put in negative because he was going downwards, where it was not close to what he had, which was 377.1. So, while the results are mildly off for the position, the velocity seems way off. Even some editing of the code and numbers I tried to make it somewhat better and it still didn't work. It was probably human error involved, specifically finding the exact temperature, air densities, and even weight of the person he had on, because there are some small inconsistencies that could lead to massive changes. Errors that could have happened. It was human error finding the right data of the drop. I maybe messed up somewhere with the coding, maybe rounded it a bit too much, was not precision with all factors in, not being exact in the expected versus the result. But what if? So, what would happen if the drop were to theoretically happen in a vacuum? Well, there would be no drag force, and he would reach close to 900 meters per second before he hit the ground. That will hurt. How much total work would happen on him from that height? Theoretically. Well, work is a force times by the distance done. So, W being mass times gravity times D, I'm saying from all the way up there to the ground is 170.78, which is his weight, times by 9.8 times by 3,869.4, gives us 44,878,034.14 joules of energy, which is a lot. Well, thank you for watching.